Hello, and welcome to lesson 6.5, the last one in this unit, where we're going to talk about woo-hoo, it's been a long day already, y'all. Molecular structure rules. So basically, these are the rules as to how and why molecules are shaped the way they are. The theory is called the VSEPR theory. We will define what that means here in a second. But the structure of particular molecules are incredibly important um, in determining how they function. Like, take water, for example. We've talked about the polarity of water and how that means that it will dissolve a lot of things and that gives it its surface tension. We've talked about how soap breaks that up, different things. But that would not happen if water wasn't shaped the way it was. I know in biology you guys talked about enzymes and you talked about how catalysts and different things like that fit together perfectly, and how body systems would not work if molecules were not shaped the way that they are. It is hugely important in how things work to know how their structure is shaped. Um, so, like it says here, scientists use a simple model called, I'm going to write it all down, valence shell. That's the V and the S. Right? We all know what the valence electrons are. They're the outermost shell, right? VALENCE, valence shell. The E is electron. The P stands for pair. So electron pairs. We talked about lone pairs and bonded pairs and stuff like that. But valence shell electron pair repulsion is the R. Um, Repulsion. Because electrons are negatively charged, right? And those negative charges repel each other, right? They don't want to be close to each other. You've all taken two magnets and put the two positive ends together or the two negative ends together, and try as you might, you can't stick them together, right? So those negatively charged electrons want to be as far away from each other as they possibly can. They are repulsed by each other, they repel each other. So those electrons repel each other, and that is what gives a molecule its shape. That's basically, like it says, the simple model. That's it. Right? So, like it says here, in the VSEPR model, the structure around a given atom depends mostly on minimizing electron pair repulsion. So, what is the place where the electrons are as far apart as possible? Far apart as possible. Still being bonded together, right? They've got those bonds, so they can only go so far, but they need to be as far apart as possible. Okay. And when we talk about this, double bonds, DOUBL, double bonds, and triple bonds are counted just like a single bond. There's no difference. If it's a double bond, triple bond, just single bond, doesn't matter. Bond, electrons, they all work the same. Again, we said it was a simple model, right? Um, so here are the steps to figuring out the structure of a molecule. First, draw the Lewis structure. Remember, that's with the dots for the valence electrons. 2, count the electron pairs and arrange them as far apart as possible. 3, determine the positions of the atoms from the way the electron pairs are shared. Okay. Lone pairs repel each other the most. And then from there, you can figure out the name. I will show you the names of the different shapes as we go along here. There's quite a few of them, but we're 5 to start out. Anyway, we'll go through these, and then I will give you a cheat sheet that you'll be able to use that has all of this information on it. You'll be able to use it for tests and things like that. So the first shape is linear. Linear happens if there are two bonded pairs and no lone pairs around the central atom. That's linear. Okay? So it's a straight line, linear. The angle degree is 180. Basically, you have the central atom, and then there are two things bonded to it, and no lone pairs on the central atom. So our examples are BeH2, beryllium hydride, carbon dioxide. So you have beryllium, Be, which has two valence electrons, hydrogen, which each have one valence electron. So we get a bond, a bond. There's no lone pairs, nothing left over. It's linear in shape. Same with carbon dioxide. Carbon's in the middle, right? Usually the first one's in the middle. It has 4 electrons, valence electrons. Oxygens each have 6 valence electrons. So we get the double bond. That makes 8 around carbon with these 2 double bonds, 2, 4, 6, 8. And 8 around each oxygen, 2, 4, 6, 8. Lone pairs on the oxygen, but no lone pairs on the carbon. Right? So linear shape. The next shape is called trigonal planar. Trigonal because it's a triangle, planar because it's all in one plane, two-dimensional, flat like a piece of paper, not three-dimensional like a cube. Okay? So this time there are 3 bonds and no lone pairs. 3 bonds, no lone pairs. We basically get a triangle. The angle between the bonds is 120 degrees. And here's an example of that. The next shape is tetrahedral. So tetrahedral basically looks like this. A triangle and then one atom going up like that. With a tetrahedral, there are 4 bonded pairs and again, no lone pairs. 0 lone pairs. Like methane, CH4. So the angle between the bonds is 109 degrees. They're as far apart as possible. They make a tetrahedron. The next shape is this. It's called trigonal bipyramidal, which means there are 2 triangle pyramids. All right, like you can see here, all of these. Oops, I don't even have it on the screen, y'all. I was looking at the paper. These 3 atoms come out from the central atom in one plane. Then this one like goes above, and this one goes below. If I could show it, like these 3 would be like a flat piece of paper, and this one would be coming up out of the piece of paper, and that one would be going down through the piece of paper. You have an assignment where you're going to be using your clay to make some of these, so you'll see how that works. This time there are 5 bonded, 1, 2, 3, 4, 5, and again, no lone pairs. So we get this triangle, and it's like 2 triangle pyramids with their bases stuck together. One going this way, one going that way. The last shape, an octahedron. That's an 8-sided figure, right? Again, this time we have 4 molecules that are flat and 4 atoms, that are flat around the central, and then one going up and one going down. So this time we have basically 2 4-sided pyramids base to base. But octahedron has 6 bonds, 1, 2, 3, 4, 5, 6, and also no lone pairs on that central atom. Okay. So those are the 5 shapes. Let's talk about expanded octets here for a minute. Central atoms from period 3 or higher. So periods are the rows, right? So we're talking like potassium, any cesium, francium, those transition metals. Um, Sometimes they can form what we call expanded octets, which means the central atom has more than 4 atoms it can bond to. So there's more than 8 electrons around that central atom, right? Remember the octet, there can only be 8. When we get up to some of the bigger ones, they can be expanded to have more than 8. So if that central atom has 5 electron pairs, it's a trigonal bipyramidal structure, same as this. If the central atom has 6 pairs, the octahedron. Right? So those are expanded octets. You can see there are more than 8 electrons around those central atoms. Try this practice one, and I will record a video showing you the answer so you can check your answer. But try this practice exercise.